Okay, it's time for us to get started. Hello and welcome to this edition of our global webinar series. Today's topic is considerations to AC rate MLCC for power applications. My name is David Adib and I am a senior technical marketing engineer here in Florida with KEMET, and I will moderate today's webinar. We're very pleased that you find time to join our webinar today. Our presenter today is Hernando Amezquita, technical product specialist, joined by Mark Lapps, who is a technical product manager. With this information, I hand it over to Hernando. Hello, Hernando. Thank you for your time today. Please tell us a little bit about yourself before you begin your webinar.
Hi, David. Thanks for the introduction. Well, welcome everybody to this webinar where we are going to talk about some considerations to AC rate and MLCC for power applications. As David already introduced me, I'm Hernando Amezquita and I'm technical product specialist for the ceramic business group. And I have been working in KEMET in different roles as process and quality engineer, also as project manager for new products introduction. And now I'm working as a technical product specialist. But let's start with the agenda that we have for today. So we're going to talk about some power basics. We are going to go through it very quickly. Some power applications, some trends, and some requirements for power applications. Then we're going to get a little bit more technical with considerations to AC voltage rate at MLCC. And then at the end, we're going to review part of the offerings that we have as KEMET for high power applications. And then at the end, as David mentioned, we're going to have a Q&A sessions. So let's start with power basics. And let's start with this review using this water analogy that you probably already know. So in this analogy, the water flow can be considered as the rate or the speed, and the power, the water pressure could be considered as the force, the water flow as the rate or the speed, and then the power could be considered just as the water times the flow rate. So if we think in different examples of hoses, we can think on a garden hose where the pressure is very low and the water flow is probably medium. So we have relatively low power. And then if we think on a pressure washer, there we have a much higher pressure, right? Than which is a higher pressure, but the water flow or the rate is still, relatively low. So you are not really getting much more power there. But if we think in the example of a fire hose, there we have higher pressure, higher rate, and therefore higher power, right? Now, if we look to the simple electrical circuit, where we can see there are voltage, which is a battery, and then we have a resistance, which helps us to determine what current is moving through the circuit. So we have the voltage, which represents the force or the pressure, the current, which is the rate or the flow, and then we have the power, which is the voltage time the current. And here below in the table, for example, in this table, we have different scenarios. Scenario A, where we have 1 volt with 10 amps, and that gives us 10 watts of power. Scenario B, where the voltage is 10 volts with 1 amp, and that's still giving us the same amount of power, 10 watts. And then we have the scenario C, where we have 10 volts, 10 amps, and therefore 100 watts of power. So that compared with the previous slide, with the water analogy, the fire hose could be represented in this third scenario, right? I know this is very basic stuff. Sorry, very basic stuff, but just to ground all of us, right? So if we also think about it as the power being dissipated in the resistor, this is called the I square R losses. So the power dissipated in the resistor is the current square multiplied by the resistance. So taking the data from the last slide, again, 10 volts times 10 amps, is equal to 100 watts, right? But the power dissipated is 10 amps squared times the 1 ohm resistor, and now you get 100 watts. Same amount of power, but all of this power is being dissipated in the resistor. Well, does it actually go? I mean, where does all this power actually go? Well, all this power is being dissipated as heat. So all the power here generated by the power supply is being dissipated as heat. And something important to mention here, and maybe you have already noticed that, is that if you increase the current, if you dramatically increase the current, that will also increase the power being dissipated and therefore the heat generation. So let's talk a little bit about power applications. So when we talk about power applications, it is very important to know how to differentiate them. So if we talk about low power, some of the characteristics of low power applications are a lower degree of work being done, lower current and voltages, and there is really not a lot of heat generation. I know that probably you're thinking that sometimes when you have a lot of apps open in your smartphone, it starts to generate some heat, but believe me, that is not a high power application. So when we talk about high power, we talk about high degree of work being done, much higher, definitely much higher currents and voltages, and this unwanted heat generation. So when we talk about these power applications, some of the examples are showing here as some pictures. As you can see, some automotive applications, solar energy, electric vehicles, data centers. So in these kind of applications, you need to be as efficient as possible when running this. And then if we talk about the power market, there are three trends that we follow in the power space, which are the wide bandgap semiconductors, like the silicon carbide and the gallium nitride, the MLCC resonant converters, and the resonant wireless power transfer. Now, these are completely independent because wide bandgap semiconductors is more sort of a technology that can be used, for example, combined with some other application trends like the MLCC resonant converters, but we'll look at them independently. Now, to talk about solutions for power applications, we created this, what you can see here in the slide, which is kind of a requirements matrix based on the application trends from the last slide. And this helps us try to understand what do we require out from our capacitors to serve the power market. Now, not all of these applications are equal, right? But we can kind of come up with kind of a general guide of what we need in our capacitors to serve the power market. And we're not going to go through this in detail, but you can see here two different colors in the table. The green, which is what we call critical characteristics, and that means the ones marked in green are characteristics that are critical for, or what we consider critical, and in yellow we have some characteristics that are important characteristics, but there are no critical. So you can see here some critical characteristics, like for example, the capacitance stability against the temperature and against the voltage, as well as the low ESR, for example. So here, this can be used as a reference for the different, for the three application trends that we mentioned in the previous slide. Now, with this said, we can generate what is the best choice for power applications, talking about MLCCs specifically. And we have here two columns. We have class 1 with COG and U2J dielectrics, and class 2 with X7R. And by looking into the matrix, we can see that the majority of these characteristics are green, which is excellent for class 1 COG and U2J, right? Now, this doesn't mean that you cannot use class 2 in some of these applications if that works, but you will sacrifice some of the characteristics that we have previously mentioned, like the capacitance stability, for example. Now, let's get a little bit more technical and let's talk about some considerations when working with power applications. So when we talk about AC voltage rating and current rating, there are two considerations for the AC applications. We have high AC voltages, or what we call as KEMET the voltage limited region, and the heating due to I²R losses, which is what we call as the current limited region. This is very important when we discuss about what the rated voltage is of an MLCC. So you can see here in the middle of the slide an example plot where you can see that the voltage is flat, and as the frequency increases, the voltage decreases. And then you can see also the current, and you can see that it increases until it gets till a certain frequency, and it levels off again. We're going to go a little bit more deeply in some next slides about this information. So when we look at the AC characteristics of an MLCC, and here we are looking class 1 versus class 2, we can see that here the impedance characteristics against the frequency. So we can see a decreasing impedance against the frequency until it gets to the series resonance frequency, which it starts to increase, right? In this part right here. And it's similar what you can see also with the ESR, similar effect that starts to decrease and then increase when it starts to get to that inflection point. Now, at the right, you can see, you can get a series RLC equivalent circuit where we have the inductance, the ESR, and the capacitance. And then you can calculate either voltage or current, depending on which one you want to look at it. So if you want to have the AC voltage, you can calculate that based on the AC current that is going to the part when you have the ESR, the ESL, and the capacitance. And then you have the current if you know the voltage, in which you will also calculate that using the parameters from the capacitor that you are using. So again, there are two regions that we consider as the voltage limited region and the current limited region. And let's start with the current limited region specifically and what defines that. So for the heating due to I²R losses or the current limited region, we have this equation that you can see here to calculate the AC current that is going through the capacitor based on the known voltage going through the capacitor, the ESR, and the capacitance that you are having there. So in this equation, or in this formula, omega is 2p times the frequency. And here we have to know that in this case, the ESL has a negligible effect on the AC current because it is less than 1 nanohenry. So based on this formula, it is notable that if the AC voltage is held constant and the frequency increase, it will result also in higher AC currents. And the same effect can be observed also if the capacitance increase. This means that the capacitor with higher capacitance value or operating at higher frequencies will get higher AC current. So in a simple statement, it can be said that at higher frequencies and capacitance values, even low AC voltages can generate a lot of AC current, as you can see in the example table that we have below. This table shows that with the same amount of voltage, in this case, 10 volts RMS, but an increase in the capacitance, in this case, for example, from 15 to 150 nanofarads, and an increase in the frequency from 100 kilohertz to 1 megahertz, it results into an increase of 100 times in the AC current that we have. So what all this mean? Well, if we look to the simple resistance, inductance, capacitance circuit model, the power being dissipated can be calculated in the ESR or in the resistor based on the I² losses, as you can see in the formula that is below the circuit. And that calculated power being dissipated can be multiplied by the thermal resistance of the MLCC that you can see there expressed as R theta. And this in order to calculate the temperature rise in the component based on the application conditions that you are having in your circuit. So the graph that you can see at the top right with different colors and showing low risk, medium risk, and increased risk shows exactly that. There is temperature areas based on the table that you have below in the slide, which are let's say the recommended temperatures to avoid any risk for thermal runaway. So this basically can be said that to maintain an optimal operating conditions of the MLCC, the temperature should be below the 25 Celsius degrees. And in the middle, you can see an example of how this can be calculated based on the ESR, the thermal resistance of the MLCC, the current, and then you can calculate the temperature rise. Now, we are not going very deep into what is thermal resistance, but there are some important things to mention here. And one of these important things to mention is that the thermal resistance is directly related to the construction of the MLCC. And how do we get it? Well, honestly, it is not easy, but we can say that the thermal resistance of the MLCC is a combination from the thermal resistance of the electrodes and the thermal resistance of the ceramic and also of the termination. So we can say that it's kind of a network of thermal resistances that you have to combine together to get the total resistance or thermal resistance of the device that you are using. And then something important to mention is that it is not only about the MLCC by itself. It is important to mention that there are some external factors that can also affect the AC current performance, because it is not just dependent on the I2R losses. It is also dependent in some kind of external factors like the ambient temperature that you're having, the thermal characteristics of the PCB that you're using, if you are having or not active or passive cooling for the MLCC, and also the proximity of the MLCC to some other sources of heat like any other kind of devices or semiconductors. This means that the thermal resistance or the total power dissipation of the MLCC is highly dependent upon how the heat is being get out of the MLCC. So this means if more power is desired to be managed by the MLCC, it is important to have a good thermal management system in your circuit. And just as an example, this is the same theory that when using a transistor, right? Nobody operates a transistor at high power without using some sort of thermal management. It is the same case here. Now, it's turn to talk about the voltage limit region. Remember that we mentioned that we have these two regions, the voltage limited region. And as shown in the graph, at lower frequencies, the voltage remains the same. And in this case, more voltage is not recommended because in the current limited region, the amount of power being dissipated is not high enough to overcome 2 voltage rules that we have as KEMET, or that we suggest to follow to AC rate and MLCC and the maximum voltage recommended. So now we have the same formula used for the AC current can be used also for the voltage calculated for the voltage calculation, but now based on the AC current and the impedance of the capacitor. So in this case, also the ESL has a negligible effect because it is less than 1 nanohenry. So based on this formula, it is notable the effect of the frequency and the capacitance that it is inverse than with the current. This means that if the AC current is held constant and the frequency decrease, or if we have lower frequencies, it will result in higher AC voltage. And the same effect can be observed also if we have lower capacitance, right? It will result also in in higher AC voltages. This means that even if the ripple current does not cause excessive heating, the peak AC voltage needs to be considered. So let's talk about these two rules that I mentioned previously. So now it's time to talk about that. So we have the peak voltage, and just to refresh our minds, the peak voltage is the peak-to-peak voltage divided by 2. So we have the rule number 1 that stands for the peak voltage of the AC waveform plus the DC voltage must be less than the rated voltage of the MLCC. So we have the peak voltage plus the DC voltage and the DC rated voltage of the MLCC marked in red, as you can see in the graph. And now in a real case scenario, let's suppose that the peak voltage plus the DC voltage is 170 volts. That means that the capacitor that we will choose needs to be DC rated above that 170 volts, right? Then we have the second rule. This second rule stands for the peak voltage of the AC waveform must be less than the rated DC voltage of the MLCC divided by 2, which according to the previous formulas can be translated into the RMS voltage that must be less than the rated DC voltage of the MLCC over 2√2. So this second rule is the rule that we have seen, like that is the most popular used in the industry to AC rate an MLCC. So in this case, as you can see in the slide, we have the peak voltage in green and the rated DC voltage in red. Right now, let's take the peak voltage and suppose that it is something like 100 volts. If we apply the formula, this means that the MLCC needs to be about 200 volts. So for example, in this case, we can pick at 250 volts for this scenario, right? And now a quick example just by considering the voltage and specifically using the second rule. If the peak voltage in this case is 520 volts, that means that the rated DC voltage of the MLCC needs to be 2 times the peak voltage. That is above 1040 volts. In this case, for example, we pick up a KC link part number 2220 chip size, 12 nanofarads, and 1200 volts rated. And now let's talk about some of, let's take a quick review or a quick view into the KEMET ceramic solutions for power applications. And we will really focus on class 1. This doesn't mean, as I mentioned before, this doesn't mean that there is a restriction for using class 2 if that works for your application. But let's remember the metrics that we saw in some previous slide where the characteristics of the class 1 dielectrics fits much better for power applications. So what solutions do we have for that? And let's start with the KEMET proprietary class 1 BME dielectric technology. We have an excellent capacitance stability with temperature and voltage, very low ESR and ESL, and high ripple current handling capability and high mechanical robustness. So the modulus of rupture, or MOR, is almost twice compared with the X7R. So this means that it is a very strong dielectric, right? So this is our base technology. So based on this technology, we created COG and U2J, some of the dielectrics that I mentioned before. And we can also create COG, surface mount MLCCs, which has a voltage range of 10 volts to 10 kilovolts. And we offer that in commercial and automotive grade. And we also developed KC Link, which is again also commercial and automotive grade, from 500 volts to 2 kilovolts. And also we have KPS MCC and KPS MCL and U2A surface mount MLCCs from 10 volts to 50 volts, again, both commercial and also automotive. And now we have also a new technology that is helping us to combine with this dielectrics that I mentioned before, that is the Connect technology, which is a high density packaging technology. And we can make COG surface mount MLCCs with Connect. This is coming for the 2021, but we are also, we are already offering this Connect technology combined with the KC link that we have. So we have KC link with Connect, and also we have U2J with Connect. This is a high density packaging technology that help us to have much capacitance, but it's not only about it. We are going to talk a little bit more about this in a few slides. So we have KC link, which we launched in 2018, but we have been releasing some additions to it this year. So as I mentioned before, it is class 1 dielectric, and we have this product available in 1812, 2220, and 3640 chip size. And honestly, we have received very good feedback from customers about this product. Then we have Connect, which is again a new packaging technology that enabling high power density by combining multiple MLCCs into a single surface mountable package, as you can see in the pictures. So maybe in a single statement, we can say that it is a technology that allows us to have more capacitance while keeping the same footprint that a single MLCC. But honestly, if we use only that description, that doesn't cover all the benefits that Connect can provide to you. So this technology uses an innovative transient liquid phase sintering technology to bond the components terminations together. So this is not using leads, right? So something important to remark about this is that Connect is not a product by itself. It is a technology that we can, as we mentioned, we can combine this with different products. Like for example, U2J, we can combine U2J with Connect, and we have Connect U2J or U2J with Connect. So one of the primary benefits of this technology is that we have also offers in some cases as low loss orientation. As you can see in the pictures, the standard or traditional orientation and the low loss orientation. And this low loss orientation provides some benefits over the standard orientation, such as lower ESR, lower thermal resistance, and lower inductance. So as you can see here that just by going into low loss orientation in the U2A with Connect, you can see in the table how we can go from 1.50 milliohms to 0.7 milliohms, and from 1.1 nanohenries of inductance to 0.45 nanohenries of inductance just by going in the low loss orientation. So when you put this in the low loss orientation, you really get that high power density of component for your application. Now, that doesn't mean that you don't have that in the standard orientation. In the standard orientation, you still getting high power, but in the standard orientation, what you're really looking for is for more capacitance in a much smaller footprint, as you will with just a single chip solution. So also you can see a thermal picture about the heat generation, right? From the different orientations that we have. And this is just an example of how it looks like. So here we have, let's say, a picture of the benefits of Connect technology. So you can see at the left, a 16x4 capacitors array. And that same array you have at the right in a 4x4 Connect low loss orientations array. So you can see here that it is very visible how much space you can save by using this Connect technology, and also some other benefits that we have by using it. So basically, this is all what I wanted to share today with you. So I don't know if there are any additional comments or questions that we have already reviewed.
So far, I don't see any questions coming in, Hernando.
Okay.
We'll give it here a minute to see if there is, if any other questions or any additional questions, I should say, will trickle in. But so far, I haven't seen any. Okay, so here's the first question that came in. What is the reason for the rule, what is the reason for rule 2 having VR times 2 VP?
I will go back to that slide.
Yeah, maybe you can go back to that slide. It says rule 2.
This is the example.
Oh, there's, yeah, actually, okay, so, yeah, rule number 2 on the right hand of the slide.
You can see it, you already can see it, right?
Yeah, I can see it, yes.
Okay, so basically this is what we have seen. This is not something that we only as KEMET use it. This is something that we have seen in the industry, and this is we can say that this is sort of how can I explain this? Obviously, the gap that you can see from the recommended DC rated voltage, right, is a safe, let's say, a safe room of operation for the AC voltage that you will be seeing, right? So you have to consider the peak AC voltage that you're having, because we know that it will be not equal, is not the same, is not equivalent to say the AC voltage to the DC voltage. So there is a room, there is a safe room of operation, and that's why the recommendation of considering this. Sorry, the person that put the question of having the 2x times the peak voltage, basically.
Okay.
Just to cut in, Hernando.
And,
yeah, so
sure.
So the rule number 1 focuses on keeping, like you said, that peak voltage plus DC voltage, keeping that below the DC rated voltage, because at no time in an application should the voltage exceed the rated voltage of the MLCC. And rule number 2, really rooted in keeping the AC portion of the waveform, or you can think peak to peak voltage less than the rated voltage. So it has to do with that oscillating of the waveform rather than just focusing on that peak. So that's the spirit of the 2 rules.
Yeah. Thanks, Mark.
okay, thank you, Mark. Thank you, Hernando. I don't see any additional questions coming in, so I think that brings us to the end of our webinar. So thank you both, Mark and Hernando, for your presentation. Thank you, everyone, for attending our webinar today. Stay safe, have a good day, and we'll see you next time. Goodbye.
Thank you. Bye-bye.